Hello, and welcome to Dreamwave Science, where curiosity sits quietly beside you, and the universe slows down just enough to feel calm, patient, and maybe even comforting as you drift toward rest. Tonight, we're going to take a gentle, unhurried walk toward one of the most remarkable discoveries of our time. It all began as a distant point in the night sky, gradually revealing itself as a doorway into some of the deepest questions humanity has ever asked, a place where light struggles to escape, where gravity feels almost unimaginable, and where our understanding of the cosmos shifted forever the moment an image appeared, an image many thought humans might never see. Tonight, as you settle in and your mind slows to its own rhythm, we'll spend time with M87, the black hole that changed everything. Let's ease into this story the same way the universe eased us into this discovery step by step, with familiar details and simple questions that help your thoughts relax. Before diving too deep, take a moment to notice where you are listening. Maybe you're at home, tucked into a cozy spot. Maybe you're unwinding after a long day, or perhaps you're half asleep, letting these words float along just enough to keep you company. Notice the time where you are. Is it late at night? Early in the morning? One of those in-between hours when the world feels quieter than usual? There's something fitting about sitting in stillness while exploring something as immense and distant as a supermassive black hole. If this gentle journey brings you a sense of calm, or if learning about the universe helps you relax as you prepare for sleep, consider giving this video a like or subscribing. It helps this quiet corner of the internet reach others who may need a soft place to rest their minds. And as always, take your time. Let your breathing find its natural rhythm. Let your thoughts wander as much or as little as you want. There's no rush, no expectation, just a slow walk through a fascinating part of the universe. Now, as we turn toward the heart of the topic, imagine that somewhere far beyond city lights, beyond the thin layer of atmosphere surrounding Earth, and beyond the familiar constellations you may remember from childhood, lies a galaxy called M87. It's enormous, ancient, and alive with activity. Trillions of stars, clouds of gas stretching thousands of light years, and clusters of material swirling and evolving for billions of years. At the center of this galaxy sits an object so heavy, so compact, and so powerful that for a long time, scientists weren't even sure it could exist in the form they imagined. Yet there it was, waiting beyond our reach, until technology finally caught up to our curiosity. Before we reach the moment when its first image appeared, it's helpful to understand how black holes approached us over time. They didn't start as dramatic scientific truths. They began as mathematical possibilities, hypotheses, ideas born from equations about gravity and motion. They were observed cautiously, sometimes skeptically. The universe is full of things we imagine long before we confirm them, and M87's black hole is one of the largest examples of this. As astronomers studied the sky, they noticed clues: stars moving too quickly around invisible centers, gas spinning in patterns hinting at unseen forces, streams of matter shooting out from galaxies at incredible speeds, as if something deep within was twisting space itself. These hints appeared slowly over years, gradually building a picture. Something massive was hiding at the hearts of many galaxies. M87 became one of the most striking examples. The story of capturing an image of this black hole is filled with small, human moments, countless nights in observatories, computer simulations running for weeks, discussions stretching into early morning hours, adjustments, recalibrations, tests, doubts, and breakthroughs. Behind it all was something simple and deeply human, a desire to understand something larger than ourselves, a longing to see what had never been seen. Surrounding that dark heart lies an immense cloud of gas and dust, heated to incredible temperatures as it spirals inward. Scientists call this the accretion flow, a glowing, swirling structure that emits vast amounts of radiation. In the case of M87, this accretion flow is so active that it influences the entire galaxy. It shapes how matter moves and how energy spreads across the region. One of the most remarkable features of M87 is the jet that shoots out from its center. Even if you've never spent much time on astrophotography, you may have seen images of it, a long, narrow beam of particles moving close to the speed of light, stretching tens of thousands of light years from the galaxy's core, like a straight line carved across space. This jet isn't created by the black hole itself, but by the complex dance of magnetic fields and matter near the event horizon. Energy builds up and escapes as a focused stream, traveling far beyond where it formed. When astronomers first noticed it in the early 20th century, it was unlike anything observed in other galaxies. From a distance, the jet may seem delicate, almost like a thin thread of light. But this is a thread of extraordinary force. Particles inside move at nearly the fastest speed anything can travel. For them, distance is measured in light years almost instantaneously. The jet carries enormous energy, shaping its surroundings and influencing the behavior of nearby gas clouds in the Virgo cluster. By observing the galaxy in multiple wavelengths, radio, visible, ultraviolet, X-rays, and more, scientists can track how the jet bends, brightens, and evolves over time. These measurements help us understand not only M87, but black holes in general. As you listen, it helps to remember that observing M87 is really looking across time. The light reaching Earth today left the galaxy roughly 55 million years ago. Back then, Earth's continents were different. Early mammals were diversifying, and the climate was shifting to set the stage for new ecosystems. That light traveled across intergalactic space without knowing it would eventually be captured by humans with sensitive instruments. So when we call M87 the giant at the center of the Virgo cluster, we're describing more than just its size and mass. We're describing its presence in the immense timeline of the cosmos. Studying this galaxy requires many tools: ground-based telescopes, space observatories, and radio arrays. Each reveals a different layer. Visible light shows its broad structure and star glow. Radio waves reveal the jet and core activity. X-rays show hot gas heated by the black hole's influence. Together, these observations create a nearly complete picture of the galaxy's dynamics. From these studies, scientists can trace the paths of high-energy particles, map gas movement in the center, and estimate the black hole's mass based on its effects. That mass is staggering. The black hole in M87 is billions of times heavier than our Sun, influencing stars even tens of thousands of light years away. Yet, compared to the galaxy itself, the black hole is tiny. It occupies a small volume, but gravity doesn't need size to dominate. Its concentrated mass warps space dramatically, bending particle paths and shaping energy flows. The region around M87's black hole is a place where matter behaves according to unfamiliar rules. Gas orbits at speeds that would tear apart ordinary structures. Temperatures soar beyond anything found naturally on Earth, and magnetic fields twist and snap, releasing massive energy. All of this motion and heat is driven by a black hole we cannot see directly. What we detect is the response of surrounding matter to its intense gravity. It took decades for astronomers to develop the techniques to study this region. Through a small telescope, M87 appears as a soft oval of light. Larger visible light telescopes show little detail. The center is too distant, too compact. That's why radio observations were key. Radio waves penetrate dust and gas, and arrays combining telescopes around the world can produce images of astonishing clarity. This was the breakthrough that revealed the shadow of M87's black hole. But reaching that point required a global network and coordination across continents. M87's story is one of astronomy and patience. The galaxy has existed for billions of years. Its light has traveled for millions. Observing it required decades of refinement. And the discovery that changed our understanding of black holes only happened because countless pieces of this long story came together. M87 waited. It lingered quietly in the night sky until we had the tools to see it closely. And when we did, what we found exceeded even our boldest expectations. As you sink deeper into this journey, remember, understanding M87 doesn't need to be rushed. Each detail builds on the next, unfolding gradually like night giving way to dawn. Piece by piece, M87 reveals itself through multiple wavelengths, careful observation, and the patient work of astronomers. Even today, scientists continue to monitor the jet, how its brightness changes, how its shape shifts, how its particles evolve. Each observation teaches us more about how galaxies like M87 function. Some discoveries confirm our expectations, others challenge assumptions, forcing us to rethink. Every piece adds clarity, showing how interconnected M87's mass, structure, jet, and central black hole truly are. The center of M87 is not just another black hole, it's far more massive, extreme, and complex than the simple diagrams or ideas of black holes in old science books. For decades, black holes were mostly theoretical, imagined through equations and thought experiments. Small stellar black holes were easier to picture, but M87's supermassive black hole defied these simple images. It is billions of times the mass of our Sun, concentrated into a volume smaller than our solar system. Gravity is so intense that even light cannot escape past a certain boundary. Yet we do not see the black hole directly. We see how it affects everything around it, drawing in matter, heating it, accelerating it, and releasing energy across the electromagnetic spectrum. Gas doesn't fall straight in, it spirals, moving at incredible speeds and reaching temperatures far beyond anything on Earth. This glowing matter allowed us to capture the first direct image of a black hole's shadow. Without it, the black hole would remain invisible. M87's black hole is unique not just in mass, but in the complexity of its environment. Magnetic fields twist as matter orbits, stretching and realigning to release immense energy, powering the jet that extends far from the galaxy's core. M87 showed that black holes are not just silent consumers of matter, they actively influence entire galaxies. Temperatures near M87's black hole reach billions of degrees, with particles moving at a significant fraction of the speed of light. Gravity is so intense here that time itself passes differently than in regions farther away. While these traits are shared by all black holes, the scale of M87 makes it truly extraordinary. Its mass extends its influence far beyond the central region. Even stars thousands of light years away feel its pull. If a solar system orbited within M87, the black hole's gravity would shape the night sky itself. For decades, scientists tried to model such a supermassive black hole using equations and simulations. But even the most advanced models struggled. The conditions near the event horizon are extreme, impossible to replicate in a lab. To truly understand M87's black hole, astronomers needed to observe it directly, or at least see the surrounding material as clearly as possible. Observing it, however, came with enormous challenges. From Earth, the region to be seen is extremely small. Despite the black hole being billions of kilometers across, its immense distance compresses it into a tiny point, like trying to spot a small object on a faraway hill. To complicate matters further, the material around the black hole is constantly shifting. The flow of gas changes, brightness fluctuates, and magnetic fields rearrange themselves. Imagine attempting to photograph something that not only sits incredibly far away, but also changes shape and intensity over time. Even if captured, the limits of resolution could leave the image blurry or incomplete. Yet scientists pursued this challenge, knowing it represented a kind of ultimate test. Capturing the shadow of M87's event horizon could confirm the predictions of general relativity, showing how light behaves under extreme gravity, and allow comparison with decades of theoretical models. As you relax into this story, picture what early scientists imagined a black hole might look like. Some thought of a simple dark sphere with a faint halo. Others imagined swirling patterns, or total darkness with no glow at all. But M87 revealed something far more structured. Its black hole shadow wasn't a simple circle, it displayed a ring of light, brighter on one side, dimmer on the other. This asymmetry comes from the motion of gas around the black hole. Gas moving toward us appears brighter due to relativistic effects, while gas moving away appears dimmer. This confirmed that matter orbits at incredible speeds, and gravity bends light around it. Before the image was captured, computer simulations predicted a bright ring surrounding a dark shadow using general relativity equations. But simulations are never the same as reality. Scientists wondered, would the gas be too turbulent? Would magnetic fields distort the image? Would telescope resolution be sufficient? Uncertainty remained even as the Event Horizon Telescope prepared for observation. When the image finally appeared, it immediately confirmed that M87's black hole is not just a theoretical concept. Its specific shape and behavior were visible. The bright ring and dark center validated decades of physics while revealing new details about black hole environments. Even the thickness of the ring provided clues about temperature, density, and motion of the material near the event horizon. Comparing these details to simulations allowed scientists to refine their models. Another remarkable aspect of M87's black hole is its stability over long periods. Smaller black holes change quickly, with matter fluctuating moment to moment. M87, with its immense mass, evolves more slowly. Structures around it shift, but not so fast that they vanish from view. This stability made it an ideal target for the first direct image of an event horizon. As you let your breathing settle into a comfortable rhythm, notice how each part of this story connects to the last. Nothing about the black hole's environment is simple. Gas motion influences brightness, magnetic fields influence motion, and the black hole's mass influences everything around it. Light emitted from nearby material navigates all these effects before reaching Earth. Some photons curve around completely, some partially, and some fall in entirely. What we observe is the collection of light outlining the event horizon's shadow. M87 also clarified how jets form. For years, scientists weren't sure how black holes launch jets at near-light speeds. Magnetic fields near the event horizon were key, but the exact mechanism was unclear. Observing M87 showed that the rotation of the black hole and the movement of matter combine to generate jets. The black hole's spin drags space around it, twisting magnetic fields and powering particle acceleration. The jet's structure, brightness, and motion confirmed this process. What sets M87 apart is its influence over the entire galaxy. In many galaxies, central black holes are relatively quiet, but M87's black hole consumes matter at a rate that indirectly emits enormous energy. Its jet carries this energy far beyond the core, shaping gas cooling, star formation, and matter distribution across the galaxy. It's not passive, it actively participates in the galaxy's structure and evolution. Even after the first image, M87 continues to challenge expectations. Astronomers refine measurements of the ring's brightness, thickness, and shape. Each new observation tests general relativity and reveals how matter behaves under extreme gravity, conditions found nowhere else in the universe. As you drift through this story, notice how the black hole is not isolated. It's part of a larger system. The galaxy revolves around it. The jet extends from it. Gas flows in. Magnetic fields twist. And light tells a story spanning millions of years. M87 is larger, more active, and more connected to its galaxy than early scientists imagined. All of this made it the perfect target for the ambitious Event Horizon Telescope project. For decades, imaging a black hole's shadow seemed impossible, but M87's size, brightness, and activity made it an extraordinary opportunity. When telescopes worldwide synchronized and collected data, scientists weren't just observing a distant object, they were witnessing a black hole that could confirm or challenge fundamental physics. Long before M87's black hole appeared on screens around the world, long before telescopes were linked across continents, and long before computers could process vast amounts of data, there were hints scattered throughout astronomy's history. Small signals, unusual motions, behaviors that didn't fit ordinary explanations. These whispered of something massive lurking in the shadows of the universe. At first, These clues didn't form a clear picture. They were fragments, collected over decades, gradually creating a trail for scientists to follow with growing curiosity. Imagine the early days of astronomy. Scientists began measuring stars' movements with precision, but they had modest telescopes by today's standards. No satellites, no supercomputers. Measurements were often recorded by hand. Yet even then, anomalies stood out. Stars near some galaxy centers moved too fast. Gas clouds swirled with more energy than expected. Something invisible seemed to tug at them, bending paths and accelerating motions. At the time, black holes were still theoretical, mathematical solutions to equations about gravity. The idea that gravity could become so strong that nothing, even light, could escape seemed extreme. Many thought black holes were curiosities of theory rather than objects that could exist. So when stars behaved oddly, astronomers didn't leap to conclusions. They recorded, compared, and ruled out more familiar explanations. Over the years, more unusual motions were detected. In various galaxies, stars near the centers moved far faster than visible mass could explain. Something compact, massive, and invisible exerted enormous influence. These early hints laid the foundation for the concept of supermassive black holes. But no single clue was enough. Scientists had to combine many observations, like assembling a puzzle without knowing the final image. For decades, that puzzle remained incomplete. Then came radio astronomy. As electronics advanced, astronomers discovered a new way to study the universe. Radio waves pass through gas and dust that block visible light. Pointing radio telescopes toward the Virgo cluster revealed a strong radio source coming from M87's direction. The emissions were far stronger than expected from stars alone. Something near the center was generating enormous energy, an important clue, because a quiet galaxy wouldn't produce such signals. Another clue emerged: a jet of material extending from M87's center. Photographed as early as the 1900s, it wasn't well understood at the time. Plates showed a faint streak, but the cause was unclear. Later, observations revealed charged particles moving near the speed of light. No ordinary star or cluster could produce this. It required extreme gravity, strong magnetic fields, and vast energy output. Once again, all clues pointed to something powerful buried in the galaxy's core, but direct evidence remained elusive. By the mid-20th century, new instruments allowed closer study of galaxy centers. Spectroscopy showed gas near M87's core moving at astonishing speeds. These weren't gentle rotations, they were high-velocity flows, accelerated by gravity far stronger than any normal object could create. If the center contained a dense cluster of stars, collisions and heating would have disrupted them. The only explanation consistent with the data: a massive, compact object whose gravity dominates everything nearby. Over decades, this idea strengthened. M87 became a prime example, with its signatures extreme and unmistakable. The evidence pointed strongly to a supermassive black hole, but proving it required technology beyond the era's reach. Each generation of astronomers refined measurements, improved instruments, and developed theories to explain how matter behaves under extreme gravity. Observations expanded across the spectrum. X-rays revealed hot gas energized by immense forces. Infrared unveiled structures hidden behind dust. And ultraviolet showed energetic processes impossible for ordinary stars. Combined, these observations formed a compelling case. Though the event horizon, the boundary beyond which nothing escapes, remained unseen. Theorists continued to refine predictions. How should light bend near a black hole? How would matter orbit in such intense gravity? What shape would a shadow cast by a black hole's glowing surroundings have? By the 1990s, simulations suggested that a black hole with an accretion flow should produce a bright ring surrounding a dark center, with the ring's shape depending on the black hole's mass, spin, and viewing angle. Observing such a ring could reveal these properties. The idea of seeing this ring seemed ambitious, but the hints kept building: fast-moving gas, strong radio emissions, the powerful jet, and light behavior all pointed toward the same explanation. M87's core was not ordinary. It contained an object unlike anything previously observed. The next breakthrough came not from new observation alone, but from a new idea linking multiple radio telescopes across Earth to act as a single, massive instrument. This technique, very long baseline interferometry, had been used before, but never on the scale needed to observe a black hole shadow. Scientists realized that if radio telescopes on different continents could work together with precise timing, they could produce images sharp enough to detect structures near the event horizon of a supermassive black hole. This concept opened possibilities that earlier astronomers could only imagine. It meant that the hints collected over the past century, the fast-moving stars, the intense radio emissions, the enormous jet, the swirling gas, could finally be tested directly. The scattered pieces of the puzzle could come together. Even with this new approach, the challenge remained immense. The signals were faint. The region to be imaged was tiny. Data needed careful calibration and processing, but the clues were too compelling to ignore. M87 became one of the strongest candidates for a black hole that could be imaged directly. Decades of observations all pointed toward the same conclusion: if any black hole could be captured visually, it would be this one. As you relax into this part of the story, it helps to appreciate how gradual scientific understanding often is. Moments of excitement exist, but most discoveries build slowly, piece by piece, with long stretches of uncertainty in between. M87's story exemplifies this slow accumulation of knowledge. Each observation deepened the picture. Each improvement in instrumentation revealed more. Each refined theory offered a better framework for interpreting data. Throughout much of the 20th century, astronomers debated how to interpret the clues. Some suggested dense clusters of stars could explain the motion of gas and stars. Others proposed exotic forms of matter. But as evidence accumulated, these alternatives became less plausible. A star cluster would not remain stable under such intense gravity. Exotic matter didn't match observed behaviors. The black hole explanation consistently withstood every new test. High-resolution radio images from earlier arrays provided additional evidence. They showed the base of M87's jet in fine detail, originating extremely close to the central region. The size of the launch point and the brightness of the radio emission matched predictions for a supermassive black hole with an accretion flow spiraling inward. Slowly, a coherent picture emerged. M87 housed a black hole so massive that it redefined what scientists thought such objects could do. It wasn't just a gravitational trap, it was a central engine shaping an entire galaxy. With each passing decade, evidence grew stronger. While a direct image of the event horizon had not yet been captured, the case for its existence became one of the most robust in astronomy. The final step, an actual photograph, was still out of reach, but it was beginning to look possible. If you soften your thoughts and imagine this timeline, you can see how breakthroughs often come from long preparation. A century of clues led to the moment when telescopes around the world could connect to form something entirely new. Observations relied on every hint collected over 100 years. Without these early discoveries, scientists wouldn't have known where to look, what to measure, or what signals to expect. As the clues accumulated and theories grew more precise, the scientific community faced a challenging question: if black holes truly shape galaxies, influence the flow of matter, and bend light as predicted by general relativity, could we ever actually see the region near an event horizon? The idea of imaging a black hole had lingered for decades, not dismissed as impossible, but hovering between what scientists hoped might someday be achievable and what technology seemed capable of supporting. Slowly, almost quietly, that conversation began to shift. What once seemed out of reach began to feel like a challenge instead of an impossible dream. Challenges in astronomy often turn into projects that take years to shape. The concept that eventually became the Event Horizon Telescope did not begin with a single meeting or proposal. It started with the realization that no existing telescope could resolve the black hole shadow at M87's distance. Even the largest telescopes could only capture faint hints. The event horizon appeared too small, not because the black hole was physically small, but because its immense distance shrinks even massive objects into tiny points of light. To overcome this limitation, astronomers turned to a technique developed over the 20th century, Very Long Baseline Interferometry, VLBI. It allows radio telescopes far apart to work together, combining their data to simulate a telescope as large as the distance between them. The farther apart the telescopes, the sharper the resulting image. VLBI had been used before to study distant galaxies and quasars, but observing a black hole shadow required scaling it up like never before. As ideas progressed, scientists realized that the entire Earth would need to act as a single coordinated telescope. No single observatory, country, or continent could provide a baseline long enough. Only a global network of telescopes could achieve the resolution necessary to see the shadow of a black hole. This marked the birth of what would become the Event Horizon Telescope. In the early discussions, the focus wasn't on a name or organization, it was purely on the science. Could telescopes separated by oceans and continents be synchronized precisely enough? Could they record data accurately to capture complex signals near a black hole? Could the observations be processed to produce an actual image rather than noise? Answering these questions required experiments and cooperation across many fields: radio astronomers, engineers, atmospheric scientists, signal processing experts, theorists, and computer scientists. They needed precise timing systems, stable atomic clocks, specialized receivers, and instruments capable of recording enormous volumes of data. It was clear from the start that this was not the work of a single institution. It required global collaboration. One of the first breakthroughs came from scientists already using high-frequency radio observations to study black hole environments. They understood that the wavelengths needed to observe the event horizon were much shorter than usual, providing higher resolution but demanding extreme precision. Short wavelengths are sensitive to atmospheric interference, require highly stable equipment, and need perfect synchronization between telescopes. But if these difficulties could be overcome, astronomers could capture details that were otherwise impossible to see, finally revealing the hidden structure surrounding M87's black hole. Gradually, observatories around the world began upgrading their equipment. Sites in the United States, Europe, South America, and even Antarctica installed receivers capable of collecting data at extremely high frequencies. They added systems to store this enormous amount of information at incredible speeds. Their clocks were synchronized using hydrogen masers, so precise they drifted only a few nanoseconds over many days. Each improvement brought the global network closer to functioning as a single, enormous telescope. As you let your thoughts remain soft and unhurried, imagine what this meant. Practically, telescopes that had spent decades on local projects were suddenly part of a coordinated global system. Researchers who had focused on their own observatories joined discussions about synchronization across continents. Engineers traveled to install new hardware. Graduate students ran simulations and tests. Meetings stretched into the night as teams reviewed data, compared ideas, and planned next steps. Every element of the project required careful cooperation, aligning instruments, coordinating observing schedules, sharing techniques, and ensuring all telescopes collected data at the same frequencies at the exact same time. The network had not yet been officially named, but it was clear this was more than an experiment. It was an international observatory, formed from the combined power of telescopes across the globe. Eventually, the phrase Event Horizon Telescope began to circulate, describing exactly what the project aimed to do: observe the region near a black hole's event horizon. The description was literal, not poetic. The telescope existed to accomplish that one goal. As the infrastructure took shape, scientists began selecting targets. Two stood out: the black hole at the center of our galaxy, and the one in M87. One was closer, smaller, and obscured by dust. The other was farther away, larger, and clearer. Each had advantages and challenges. M87, with its massive size and strong radio emissions, quickly emerged as the most promising candidate for producing a clear image. Building the Event Horizon Telescope did not happen in a straight line. Some years brought fast progress, others brought setbacks. Weather interfered with tests, hardware failed, funding wavered, and computers struggled to process the enormous data loads. But for every obstacle, the teams found solutions. Methods were refined, systems upgraded, and data shared across continents. Slowly, the dream of photographing a black hole began to feel achievable. A crucial part of the project was data storage. Each telescope produced massive amounts of information, too much to send over the internet. Instead, the data was recorded on specialized hard drives and physically transported to processing centers. Technicians in remote locations, including the South Pole, carefully packed crates of drives, sometimes waiting months to ship them due to harsh weather. The data sat in frozen isolation, preserved until it could reach the correlators. Processing this data required immense computational power. At correlator centers in the United States and Germany, teams aligned datasets from each telescope with nanosecond precision. Timing errors, even tiny ones, could distort the final image. The Earth's rotation, atmospheric variations, and telescope positions relative to M87 all had to be accounted for. The final image would not be captured in the usual sense. Instead, signals from telescopes separated by thousands of kilometers had to be combined. Radio waves broken into frequency components, aligned, and reconstructed. It resembled assembling a mosaic with pieces scattered across the globe. But the mosaic was made of data, and the image would only appear after millions of calculations. As the collaboration grew, it became clear that observing a black hole required hundreds of researchers across disciplines: radio astronomers, engineers, computer scientists, atmospheric specialists, and theorists. Conferences and meetings brought these experts together. Observational astronomers worked alongside instrument specialists and theorists. Small teams merged into larger units. Emails, video calls, and shared documents kept the network connected. Every step contributed to the birth of the Event Horizon Telescope. The most defining moment came when the collaboration agreed the system was ready for its first major observations. Years of preparation, testing, and refining led to this point. Telescopes were synchronized, hardware installed, and preliminary tests passed. Scientists believed that if conditions cooperated, the network could resolve the region near a black hole. The decision to proceed carried both excitement and caution. Success wasn't guaranteed. Weather could interfere, equipment could fail, timing could drift, but the collaboration moved forward because the only way to succeed was to try. Even partial data would help refine the system, and if everything worked, it would capture information never before obtained. The Event Horizon Telescope didn't appear suddenly. It grew from decades of preparation and collaboration. Researchers contributed expertise, telescopes were upgraded, and new data processing methods were developed. Like the accumulation of clues that pointed to M87's supermassive black hole, the telescope was the culmination of slow, persistent effort. Once the network was ready, the focus shifted. Not only did the instruments need to function, but the Earth itself became part of the telescope. The planet had to act as a single, coordinated eye pointing toward M87. Timing had to be perfect, and cooperation had to be unmatched. This was the only way to see the shadow of a black hole 55 million light-years away. Observations relied on wavelengths highly sensitive to atmospheric conditions, water vapor, temperature fluctuations, and even slight air disturbances could distort or weaken the signals. Each telescope needed clear skies, T-stable conditions, and instruments operating at exactly the same frequency. Any disruption, whether hardware or timing, could compromise the entire dataset. Scheduling observations required careful monitoring of forecasts, atmospheric models, and sky conditions for each site worldwide. Some telescopes were perched on high mountains, offering thin air but unpredictable weather. Others were in deserts, with dry air but strong winds and temperature swings. One site was at the South Pole, where winter nights lasted months and temperatures plunged far below freezing. Coordinating these environments demanded patience and flexibility. As you listen, Imagine the Earth slowly rotating beneath the sky, carrying each telescope across slightly different positions relative to M87. This rotation was a key part of the technique. As the planet turned, the baseline between each pair of telescopes changed slightly, allowing astronomers to sample different parts of the black hole's structure. To take advantage of this motion, all telescopes had to start observing at nearly the same moment. They had to track the black hole as it moved across their skies, adjust instruments in real time, and store the faint signals precisely. This is where the atomic clocks came in, hydrogen masers, keeping time so steadily that drift over hours was negligible. These clocks ensured every dataset could be synchronized later for processing. Without them, the effort would fail. The clocks didn't just keep time, they held the entire system together. As the observation period approached, teams prepared for round-the-clock operation. Many sites required special attention. High-altitude telescopes contended with thin air and rapid temperature changes, while others faced unique challenges posed by their remote locations. Some telescopes were located in remote regions far from cities, making communication and coordination more challenging. Yet each site was staffed by people who had trained for years to ensure the instruments operated flawlessly. Teams monitored weather, tuned equipment, checked timing signals, and made sure everything was ready. When the observation window opened, the telescopes pointed toward M87. Some sites were just beginning their nighttime hours, others were in the middle of the day, using radio wavelengths unaffected by sunlight. Each location followed a schedule to track the black hole as long as it remained above the horizon. As the Earth rotated, new pairs of telescopes became visible to each other, forming new baselines. The global network worked telescope by telescope, hour by hour, gathering data in a synchronized and steady motion. The telescopes recorded enormous amounts of information. Sending it over the internet was impossible due to speed limitations, so the signals were stored on specialized hard drives. These drives wrote data at incredible speeds, so only a few systems in the world could handle them. As each telescope collected data, its drives filled with information about radio waves coming from the black hole's vicinity. Signals were faint, buried in noise, but precise timing and synchronization ensured patterns could be reconstructed later. While observing, teams continuously monitored system performance. They checked frequency stability, verified receiver health, confirmed clocks were running accurately, adjusted for minor weather variations, and coordinated with other sites. In some locations, work stretched late into the night. In others, it began before sunrise. The collaboration was global in scope and in time, with overlapping shifts keeping the network fully active. As you relax into this part of the story, imagine the moment when all telescopes observed simultaneously. This wasn't just machines pointed at the sky, it was hundreds of people across countries working in harmony. The observation unfolded slowly over many hours, each participant aware that small details mattered. A cloud bank, a hardware issue, or a timing glitch could mean waiting another year for the chance to try again. After observing sessions ended, drives were carefully removed, labeled, and stored for transport. Some data from places like the South Pole had to wait months until flights were possible. Once the drives arrived at the correlators, the next stage began combining the data with extreme precision. Tiny timing differences were corrected, atmospheric distortions accounted for, and the Earth's rotation factored into calculations. Processing required massive computational power and teams of experts who understood how to align and interpret the signals. Outside the collaboration, the world waited quietly, unaware of the careful work happening behind the scenes. Scientists reviewed logs, checked for irregularities, compared processing methods, and tested imaging algorithms. This meticulous work gradually revealed what the Earth-sized telescope had captured. The process mirrored earlier steps in its patience and method. The Event Horizon Telescope did not reveal the black hole in a single moment. Observations were not snapshots. They were slowly assembled, using the Earth itself as part of the instrument. Its rotation created varying baselines. Its geography spread telescopes worldwide, and its scientists transformed these resources into a system capable of resolving a structure smaller than Mercury's orbit, tens of millions of light-years away. This transformation was not the result of one breakthrough. It arose from countless small adjustments and coordinated efforts. The Event Horizon Telescope became a planet-sized eye, the culmination of human collaboration and ingenuity. It showed what can happen when technology and cooperation combine over decades. Once observations were complete, the next step involved something less visible but equally crucial: examining the signals themselves. The telescopes had recorded faint traces of radio waves from the region around M87's event horizon, waves that had traveled millions of years before reaching Earth. They carried information about matter motion, light bending, and the strength of gravity in one of the universe's most extreme environments. The data now rested quietly on hard drives, awaiting processing. To understand this, remember that the light captured wasn't ordinary light. It was radio waves, with wavelengths measured in millimeters, emitted by electrons spiraling through magnetic fields at tremendous speeds near the black hole. These waves bent around the black hole's gravity, creating patterns of brightness and darkness that revealed the invisible boundary itself. Gathering this radiation was only the first step. The data was not a photograph. It was a record of signals over time, mixed with atmospheric noise, equipment variations, and cosmic background fluctuations. The signals had to be carefully aligned and interpreted before forming any image. Even tiny timing discrepancies could blur the result. That's why the atomic clocks at each telescope were so vital. They provided exact timestamps for precise data alignment. During processing, researchers compared signals from each telescope, searching for correlations. When two telescopes observed the same structure simultaneously, the signals matched, forming the foundation of the eventual image. As you continue listening, imagine the immense effort needed to sift through these datasets. Each pair of telescopes formed a baseline, providing a unique piece of information about the black hole's surroundings. With the global array, astronomers sampled many parts of the image, but gaps remained. Earth does not have telescopes everywhere. To complete the image, scientists relied on sophisticated algorithms to reconstruct missing information accurately. This stage required not only astronomers, but also experts in imaging, statistics, and computer science. Multiple independent algorithms were used to ensure no single method dominated the reconstruction. Each algorithm approached the problem differently, adding robustness to the final image. Some imaging algorithms aimed to find the simplest structure consistent with the data. Others placed constraints on brightness or smoothness. Some filled in missing information by comparing the black hole environment to simulated models based on physics. The goal was not to produce identical images, but to find consistent patterns across different methods. Before applying these algorithms to M87's real data, scientists tested them with synthetic datasets, simulated black hole environments, mimicking what the Event Horizon Telescope might capture. These tests refined the algorithms, revealed potential biases, and helped researchers understand how the methods behaved in different scenarios. By the time the real data arrived, the teams had a clear sense of how reliable their methods could be. Yet even with preparation, the first processing of real data carried uncertainty. No one knew exactly what the image would look like. Simulations provided expectations, theories offered guidance, and decades of hints pointed toward a certain structure. But nature doesn't always match expectations. The raw data held the truth, and it was through careful, quiet work that it would be revealed. As correlators began aligning signals, small pieces of the structure started to emerge. These weren't images in the usual sense, but patterns of brightness variation, faint hints without sharp edges. Intermediate results suggested a ring-like formation near the black hole, but the full picture remained buried among countless adjustments and calibrations. To prevent human expectations from influencing results, the collaboration followed strict procedures. Multiple teams worked independently, using different software, algorithms, and assumptions. This separation reduced bias and allowed each team to reach its own conclusions before comparison. Meanwhile, Theorists refined models, predicting how matter should behave near the event horizon, how light should bend, the likely thickness of the ring, the asymmetry caused by orbiting gas, and the expected shadow. These predictions guided the imaging teams, but did not dictate results. As more data was processed, correlations between telescope pairs became clearer, revealing the underlying light distribution near the black hole. The predicted bright ring appeared across multiple reconstructions, not identical, but consistent. The dark center, the shadow, also began to form. Noise, coverage gaps, and atmospheric effects added irregularities, but the shape matched the silhouette predicted by general relativity. At this stage, the collaboration compared independent reconstructions. Slowly, cautiously, they examined where images overlapped. A bright ring seen by all teams was likely real. A shadow consistently appearing in the same location was unlikely to be an artifact. The consistency built confidence, while differences helped refine interpretations. Researchers also compared the images to simulated models to develop physical intuition. Ring brightness varied with viewing angle and gas rotation speed. Comparing the observed asymmetry with models allowed teams to estimate the black hole's orientation and the direction of rotation, determining its spin axis relative to Earth and the galaxy. The process required patience. Each step depended on the accuracy of the previous one. Imagine quiet labs, people reviewing plots and diagrams, conversations drifting through meeting rooms, hours spent calibrating signals, days running algorithms. This was not a sudden discovery, it unfolded as a long, steady sequence, each step revealing a little more. Once confident in the consistency of independent results, teams merged efforts to produce a final set of images reflecting the collaboration's consensus. The bright ring was clear, the shadow distinct. Ring thickness matched relativity predictions. The asymmetry matched expected Doppler boosting from gas orbiting near the event horizon. Every detail aligned with long-standing theories. Before sharing the results with the world, the team confirmed that no alternative explanations could produce the observed structure. Denser star clusters, exotic matter, or other hypothetical scenarios did not match the data. Only a supermassive black hole surrounded by an accretion flow, governed by general relativity, produced the observed structure. As the analysis concluded, the collaboration grasped the significance. The ring wasn't perfect, the shadow not crisply defined, but the overall structure was unmistakable. They were seeing light that skimmed the edge of an event horizon. Shapes formed by gravity so strong that photons curved into warped paths. They were witnessing something theorized for over a century but never directly seen. The atmosphere among the teams shifted. Caution remained, but so did a growing sense of accomplishment. Years of work had converged. The Earth-sized telescope had done its job. Faint radio waves, traveling millions of light years, had left patterns that scientists could interpret. The image was real, it showed exactly what they hoped to find. Through it all, the black hole itself remained unchanged. It didn't react to being observed. It continued bending light, moving matter, and shaping its galaxy as it had for billions of years. But humanity now had a way to see its gravity in action, not the form, but the effect on its surroundings. The moment the image finally emerged was quiet and gradual. It unfolded in labs and offices, with researchers watching pixelated structures, curves of brightness, and patterns hinting at something familiar. It began with independent teams, each following strict protocols to prevent bias. Software, assumptions, and methods differed. The goal wasn't redundancy, it was protection against human influence. When the first group saw a ring with a darker center, there was silence, not celebration. They checked inputs, algorithms, and considered artifacts. A second team reconstructed independently and saw the same ring-like formation. Then a third and fourth team confirmed it as well. Step by step, patterns emerged: a bright ring, asymmetric brightness from orbiting matter, a consistent circular shadow. The images didn't have to be identical, they needed only to match an essential structure. 4 independent teams had seen the same thing. As you relax with this story, imagine the quiet excitement spreading among the collaboration. News moved in careful conversations, not shouts. Teams compared ring structures, thicknesses, brightness variations, and shadow positions. Slowly, the first direct image of a black hole took shape in human knowledge, the culmination of over a century of theory, observation, technology, and collaboration. Researchers carefully reviewed how each algorithm handled noise and missing information. When the independent images were laid side by side, the similarities became undeniable. Yet the scientists did not rush. They performed cross-checks, ran alternative imaging methods, tested against additional synthetic datasets, and examined instrumental effects that could mimic the features they saw. Calibration steps were repeated, correlations in the data analyzed, and patterns carefully compared. This wasn't doubt, it was responsible science. The image held profound implications for physics, astronomy, and our understanding of gravity itself. It could not be rushed, only after methods converged, after teams verified consistency, and after long hours of refinement did the collaboration gather to review the images collectively. This gathering was quiet and deliberate. Scientists sat in rooms or connected virtually, studying images arranged on screens, the bright ring, the dark shadow, the surrounding glow. The structure was clear. It was no longer theoretical. It was real. There was no sudden cheer, only a shared sense of something settling into place, a collective breath, the quiet acknowledgement that years of preparation had revealed what no one had ever seen. The light that had bent around the black hole's event horizon had formed a ring on their screens. The shadow was no longer a diagram. It existed as a measurable feature of the universe. Yet even then, researchers described it modestly: relief, quiet excitement, a touch of disbelief. There were smiles, gratitude, but the atmosphere remained grounded. Science often moves slowly. Breakthroughs rarely feel dramatic. They unfold as a culmination of steady work, step by step, until the result becomes undeniable. Over the following weeks, the collaboration refined the reconstructions into a final image for publication. This involved reviewing consistency, combining the strongest elements of each independent result, and producing a version that accurately reflected the data. Every detail mattered. The image needed to be understandable to the public, trusted by scientists, and transparent enough for others to trace the methods used. Teams debated how to present the brightness profile, how to show asymmetry from relativistic gas motion, and how to represent the ring's thickness and uncertainties. The goal was not a perfect picture, but a truthful one. Meanwhile, the world outside the collaboration remained unaware that something extraordinary had already been captured. The data was kept private, not from secrecy, but from adherence to scientific standards. Verification and careful discussion were essential before public release. Researchers continued working quietly, refining details, drafting papers, describing methods, data, algorithms, uncertainties, and physical interpretations. Writing took time, but it was part of the responsibility. Sharing the image meant sharing everything that supported it. Teams also prepared for the public announcement. They worked with science communicators, designers, and press coordinators to explain the image clearly to a wide audience. Many had never heard of M87, the Event Horizon Telescope, interferometry, or radio astronomy. The goal was to bridge technical details and the sense of wonder the image could inspire. Researchers practiced explaining the ring and shadow in simple terms, rehearsing presentations for journalists and general audiences, conveying excitement without compromising accuracy. In the final days, teams double-checked the image, reviewed papers, finalized press materials, and coordinated presentations so scientists across continents could speak simultaneously. Then, the moment arrived. On announcement day, the world watched as scientists stood before screens, displaying the now famous image, a bright ring surrounding a dark center. The shadow cast by M87's supermassive black hole. The ring matched predictions from general relativity. Its size corresponded to the mass calculated from decades of observations. The asymmetry reflected the motion of matter orbiting near the event horizon. People reacted in many ways: astonishment, curiosity. For many, it was the first time they had ever seen anything related to a black hole. Though the image was blurry compared to everyday photographs, it represented something profound, the first direct visual evidence of a black hole shadow. It confirmed ideas proposed over a century earlier and provided a tangible connection between theory and observation. The image circulated worldwide through news, social media, and scientific discussions. Even those unfamiliar with astronomy recognized the ring of light. It sparked conversations about gravity, space, and the universe, demonstrating what humans can achieve through global collaboration. Inside the collaboration, the mood was reflective and celebratory. Researchers recognized decades of work, contributions of colleagues who had developed theories, simulations, and technologies, and the global nature of the accomplishment. Yet the image was not the end. It was a milestone and a beginning. The data held more secrets. The image could be refined. The telescope network could expand. Other black holes could be observed. The work would continue, slowly revealing new details and raising new questions. The moment the image appeared was not dramatic or cinematic. It was defined by careful science, patient effort, and quiet realization. The bright ring was more than a feature of a distant galaxy. It was evidence of gravity behaving exactly as predicted under extreme conditions. The image of M87's black hole became known as a ring of fire, not literal fire, but glowing matter accelerated and heated by extreme gravity. It marked the boundary between visibility and invisibility, between brightness and darkness, between what we can observe and what exists beyond our reach. In a quiet, steady way, that ring of light changed human history. To understand why it resonated, imagine the anticipation built over more than a century. Scientists theorized black holes long before evidence existed, predicted event horizons, calculated how light would bend, and worked out space-time curvature around massive objects. But until the image, all of that lived in equations and models, real in theory. Not in the tangible way a photograph makes something feel real. The image of M87's black hole was the moment those theories crossed into reality. The ring of light was not a diagram, an artist's impression, or a simulation. It was data from the universe itself, recorded by telescopes across Earth. Its shape and brightness matched general relativity precisely. The dark center marked the region from which no light could escape. For the first time, humans could see what happens at the edge of a black hole, bridging a gap that had existed since physics' earliest days. The ring of fire allowed scientists to test general relativity under extreme gravity. Previous tests, Mercury's orbit, starlight bending, pulsar timing occurred in weaker gravitational fields. The M87 shadow provided a direct test in the strongest gravity accessible. Its size, shape, brightness, and asymmetry aligned with predictions. The bright side of the ring reflected Doppler effects from gas orbiting near light speed. Ring thickness revealed the distribution of hot gas near the event horizon. Everything aligned theories, observations, and reality. As you let yourself sink further into this story, you might notice that the significance of M87's image wasn't purely scientific, it was cultural. It reached people who had never studied astronomy, physics, or cosmology. The image appeared on news broadcasts, magazine covers, classrooms, social media, and in conversations between people who had never discussed black holes before. It became a universal symbol of discovery, representing the mysteries still waiting in the universe and showing that humans, through curiosity and cooperation, can reach beyond previous limits. The ring also carried emotional weight. Some saw it and felt a sense of scale, realizing how small Earth is compared to the immense structures of the cosmos. Others felt a sense of connection, imagining light that had traveled millions of years to appear on a screen. Some viewed it as a reminder of how far science had come, from glass and metal telescopes to a global network functioning as a single instrument. The moment was not only about physics, it was about human creativity, persistence, and collaboration. Within the scientific community, the image had additional importance. It provided direct evidence that supermassive black holes exist as measurable structures, not just inferred objects. It confirmed that accretion flows behave predictably near event horizons, validated assumptions in simulations, and allowed theorists to refine models with new data. The image also opened the door to future measurements, observing the black hole at different frequencies and times, tracking changes in the accretion flow, measuring magnetic fields, and studying matter motion in one of the universe's most extreme environments. Beyond science and culture, the Ring of Fire demonstrated what global collaboration can achieve. The Event Horizon Telescope was not the work of a single country or institution. Observatories across continents, researchers from diverse fields, and teams working together across enormous distances made it possible. The collaboration became an example of how shared resources, planning, and expertise can produce remarkable achievements. When the image was released, people celebrated not only the result, but the process behind it. They saw the value of networks spanning borders, how different cultures and institutions could work toward a common goal, and how young scientists, experienced researchers, engineers, technicians, and students all contributed. Challenges that once seemed impossible became achievable through patience, cooperation, and long-term dedication. One subtle way the image changed history was by shaping how people imagine black holes. Before, depictions mostly came from movies, animations, or artistic interpretations, often stylized, dramatic, or exaggerated. After the image, the glowing ring became the standard reference for what a black hole looks like when surrounded by glowing matter. It entered the visual language of science, inspiring curiosity, education, and art. Teachers used it for lessons. Students wrote papers. Artists incorporated it into their work, and writers referenced it in books and articles. Within the collaboration, the image sparked new research directions. Scientists planned observations at higher frequencies, considered adding more telescopes to improve resolution, and studied long-term changes in the ring. The image was a beginning, not an end point. Imagine the researchers reflecting on years of work, early hints, accumulated evidence, development of interferometry, telescope construction in remote locations, careful planning, and meticulous data analysis. The Ring of Fire was not just a technological achievement, it was the product of persistence. For decades, black holes were known only through their effects on stars and gas. The event horizon itself was considered unseeable. Theoretical papers often claimed imaging a black hole was impossible. Yet, by capturing the glowing material just outside the boundary, the Event Horizon Telescope revealed the silhouette, the closest humans could come to seeing an event horizon. Seeing the shadow transformed how scientists think about observation. Invisible objects can leave detectable traces. Boundaries that seem absolute may still offer clues. The ring also highlighted the role of computational astronomy algorithms, signal processing, and software-combined data recorded across the planet. Modern astronomy is as much about data science and simulations as it is about lenses and mirrors. Coding, mathematics, engineering, and observational skills all contributed to this discovery. Although the world reacted strongly to the image, the scientists remained grounded. Many emphasized humility. The image was only one black hole. The universe holds countless others. The ring raised more questions than it answered about light behavior, dye motion, shadow formation, and black hole rotation. This was the essence of science. Progress comes from questions emerging when answers are finally found. As you rest with this story, consider how the Ring of Fire bridged past, present, and future. It connected a century of theory to a moment of observation, turning mathematical predictions into visual reality. It paved the way for future studies of black holes, gravity, and the structure of space. The ring didn't change history through drama or brightness. But through understanding, it was steady, collaborative, and built from light that traveled millions of years. The release of M87's black hole image prompted global curiosity. The glowing ring carried answers scientists had sought for more than a century. It confirmed the existence of black holes, revealed how space behaves near them, how time stretches, and how gravity operates under extreme conditions. In a gentle, steady way, M87 allowed humans to understand the universe more clearly. Imagine the environment around M87's black hole gas heated to extraordinary temperatures, magnetic fields twisted by rotation, and particles moving near light speed. Here, gravity is so intense that time itself behaves differently. Near a black hole, gravity alters the geometry of space, bends light paths, and slows time. The ring of light surrounding M87's shadow illustrates gravity not as a simple force, but as the curvature of space-time. Light normally travels straight, but near a massive object, space curves, and light bends. Near Earth, this effect is tiny. Near the Sun, light bending is noticeable only during eclipses. Near a black hole like M87's, bending is extreme. Photons can orbit briefly before escaping, forming the ring-like structure that outlines the event horizon. This behavior, predicted decades earlier, had never been directly observed until the Event Horizon Telescope captured the image. M87 confirmed that light behaves near a black hole exactly as general relativity describes. Its shadow's diameter and ring structure matched predictions for a black hole of M87's mass. Relativistic effects, brightness asymmetry, and ring thickness revealed gas motion and distribution. Everything aligned, theory and observation united. As gas spirals closer to the event horizon, it orbits faster and experiences increasingly intense gravitational effects. From the viewpoint of a distant observer, the gas seems to slow down as it approaches the horizon, even though locally it continues moving rapidly. This interplay between local motion and distant observation creates the brightness pattern we see. The side of the ring moving toward Earth appears brighter, an effect known as Doppler boosting, while the side moving away appears dimmer. The clarity of this pattern in the image provides further confirmation that relativity accurately describes matter's motion in these extreme conditions. The image also illuminates the structure of spacetime near the event horizon. The shadow is not a surface, because black holes have none. Rather, it marks the boundary beyond which light cannot escape. The central darkness represents an absence of light, a silhouette formed by curved spacetime itself. The surrounding ring is created by photons skimming the edge of this boundary, temporarily held in orbit before escaping. This delicate balance of light and dark directly illustrates the event horizon, answering long-standing questions about whether black holes truly possess this boundary. The darkness matches predictions light from within cannot escape, confirming black holes as genuine space-time structures, not merely dense objects with unusual properties. Beyond light and time, M87's black hole reveals how black holes shape galaxies. Energy from the accretion flow and the jet influences the galaxy as a whole. The jet, extending thousands of light years, carries energy that affects gas clouds and star formation. Black holes are not isolated, they actively connect to the evolution of their galaxies. M87's jet is a vivid example of how black holes regulate their environments. Understanding the jet's physics helps scientists study magnetic fields near the event horizon. The jet is powered by the black hole's rotation and magnetic fields within the accretion flow. As matter spirals inward, it drags magnetic fields into tight, twisted loops, storing energy like a stretched elastic band. Under the right conditions, this energy is released as an outflow of particles. The black hole's rotation, twisting spacetime itself, further accelerates particles along these magnetic field lines, producing a narrow, focused beam of matter and energy shooting outward at astonishing speeds. In M87, this jet is exceptionally large and observable across many wavelengths, from radio to visible light to X-rays. Astronomers have studied it for over a century, long before the Event Horizon Telescope captured the black hole's image. Early photographs from the 1910s already showed a faint streak of light extending from the galaxy's core. Over decades, as telescopes improved, the jet's structure became clearer. It is composed of charged particles moving near the speed of light, guided and confined by magnetic fields. The scale of the jet is almost incomprehensible. It stretches tens of thousands of light-years from the galaxy's center. Traveling along it at the speed of light would take thousands of years to reach the point where it fades into intergalactic space. Yet, from Earth, the jet appears as a delicate line, a thin structure visible in long-exposure images. This contrast between immense physical size and subtle visual appearance is one of the many wonders that astronomy reveals, highlighting the extraordinary forces shaping our universe. Enormous cosmic structures can appear fragile, while tiny regions can seem dominating when viewed up close. As you relax into this part of the story, imagine following M87's jet as it streams outward from the black hole. At its base, the jet is narrow, compact, and incredibly bright in radio wavelengths. So intense is this radiation that the launch region has become one of the most studied sites in all of radio astronomy. As the jet extends outward, it gradually widens but remains tightly focused, guided by magnetic fields that wrap around it, preventing rapid dispersion. Without these magnetic fields, the jet would quickly lose its structure and spread into a diffuse cloud. The jet is not uniform along its length. It contains knots and bright spots, caused by variations in density and magnetic strength. Over time, these knots move along the jet, revealing the speed of particles and the energy that drives them. Some knots appear to move faster than light, an optical illusion resulting from relativistic effects due to the jet's orientation and extreme speed, reminding us just how fast these particles travel. Near the speed of light, one of the most remarkable features of M87's jet is how it remains coherent across vast distances. As it interacts with surrounding gas and dust, it produces shocks that heat the material and create emission regions detectable by astronomers. These observations provide information about the density and structure of the intergalactic medium, revealing the environment around the galaxy. For scientists studying galaxy evolution, these details are invaluable. They show how energy from the black hole influences areas far beyond the central core. The jet is also part of a feedback system. Energy carried by the jet affects gas behavior, star formation, and matter distribution. In some galaxies, jets heat gas so much that it cannot cool and condense into new stars, demonstrating how black holes can regulate star formation on galactic scales. Observations of M87 have shown just how powerful this feedback can be, influencing clusters of gas both inside and beyond the galaxy. Closer examination of the jet provides insights into the black hole's spin. The jet aligns with the rotation axis of the black hole because the spin dictates the orientation of magnetic fields that launch the flow. Measuring the jet's direction and stability allows astronomers to infer how the black hole rotates. Spin affects how much energy can be extracted through magnetic fields and how stable the accretion flow remains. Even though the jet has been observed for over a century, modern high-resolution images reveal the base in remarkable detail. They show how the flow begins near the event horizon and how magnetic fields behave. Observations confirm that the processes driving the jet align with predictions from general relativity and magnetohydrodynamics. The jet helps us understand how energy is distributed in the universe. Much of the radiation from distant galaxies originates from jets powered by supermassive black holes. The energy carried by M87's jet, though only a fraction of the black hole's total energy, is sufficient to shape structures far larger than the galaxy itself. Imagine a narrow beam of particles traveling thousands of light-years, guided by magnetic fields and the black hole's rotation, interacting with clouds, shocks, and intergalactic gas, leaving visible imprints along its path. The jet also demonstrates long-term stability. Observations show it has persisted for millions of years, reflecting a balance between matter inflow and outflow, and between gravitational pull and magnetic forces. This cycle shows that the black hole is not consuming matter in bursts, but sustaining energy production over cosmic timescales. Polarization studies add another layer of insight. Light from the jet is polarized, meaning the electric and magnetic fields of the waves have a preferred orientation. These patterns allow scientists to map magnetic field structure, showing that fields are well-ordered and essential for launching and maintaining the jet. Recent polarization imaging by the Event Horizon Telescope has revealed how magnetic fields thread through the accretion flow, confirming theoretical models. It becomes clear that the jet is not a secondary feature. It is central to how M87's black hole interacts with its galaxy, revealing the black hole's spin, magnetic field strength, accretion flow structure, and energy distribution across the galaxy. The jet connects the small scale near the event horizon to the vast scale of the galaxy itself. The jet illustrates the interconnectedness of cosmic structures. Starting in the environment near the event horizon, it extends into the intergalactic medium, shaping gas, influencing temperatures, and guiding star formation. It is a bridge between scales, showing how local processes can have global effects across the universe. Even now, mysteries remain. Scientists continue to study how particles are accelerated to near-light speeds, how magnetic fields remain stable over thousands of light years, and how the jet maintains its structure. Observations at different wavelengths, combined with refined models, reveal new details each time, guiding researchers toward a deeper understanding of matter, energy, and space-time near a supermassive black hole. Through M87's jet, the story of black holes expands, connecting ring, shadow, accretion flow, space-time curvature, and relativistic effects into a framework we understand increasingly well. Yet around every answered question lies a larger world of physics still to be explored. The closer we get to understanding black holes, the more their mysteries unfold. M87 has shown us incredible detail, but it also exposes gaps in knowledge and deeper layers yet to be discovered. This is not a failure, it is part of how science progresses. Every discovery opens the door to new questions. As we look at M87 closely, we see not only what we understand about black holes, but also what remains uncertain. This section of the story is quieter, more reflective, because it explores edges of our theories, edges of our models, and edges of what our instruments can currently reveal. Step back from the specific observations for a moment. The shadow, the jet, the magnetic fields, they all fit within Einstein's general relativity, a framework that has successfully predicted phenomena for over a century. Yet, even a theory as powerful as relativity is not complete. It does not fully describe the physics at the most extreme conditions, and black holes are among the universe's most extreme objects. One profound mystery is the singularity at a black hole's center. Classical relativity predicts that space collapses to an infinitely small point with infinite density, hidden beyond the event horizon. We cannot observe it directly, and perhaps the math's infinities signal the limits of our theory rather than reality. This is the first hint that M87 pushes us toward physics we do not yet fully understand. Something must occur before reaching infinite density, some law beyond current theories, often called quantum gravity, which aims to merge relativity and quantum mechanics. Black holes serve as natural testing grounds for this missing theory. Another unresolved puzzle is the information paradox. Classical relativity suggests that any information about matter entering a black hole is lost forever. But quantum mechanics insists information cannot be destroyed. M87's image does not resolve the paradox, yet it provides context. The event horizon behaves as relativity predicts. But what happens to information that falls in? Does it remain encoded at the horizon? Does it escape subtly? Or does a future theory of quantum gravity answer the question entirely? Then there is the jet. We understand broadly how magnetic fields and black hole rotation launch it, yet the precise mechanics remain elusive. How does the jet maintain its coherence over thousands of light years? How are particles accelerated to near light speeds? What role does turbulence in the accretion flow play in shaping the brightness, thickness, and motion of both the jet and the ring of light? Even the black hole's spin is only partially constrained. Spin affects the structure of spacetime near the event horizon, energy extraction, and accretion stability. Yet measuring it precisely is difficult. The thickness of the ring, predicted differently by various simulations, sits between expectations, suggesting a complex interplay between turbulence, magnetic fields, and relativistic motion. The photon ring, formed by light orbiting the black hole multiple times before escaping, remains blended with the broader emission, its brightness sensitive to conditions we cannot yet fully resolve. Future higher resolution observations may reveal more, providing tests of relativity at even finer scales. M87 also invites deeper questions about the nature of spacetime itself. While relativity treats it as smooth and continuous, quantum theories suggest it may be granular or fluctuating at extremely small scales. Black holes could reveal this structure, though current instruments cannot yet detect it. As technology improves, scientists hope to observe finer structures near the horizon, potentially uncovering new physics. Quantum fields near the event horizon add further intrigue. Particle-antiparticle pairs form and annihilate constantly, yet near a black hole, this process may produce Hawking radiation, causing slow black hole evaporation. We have not observed it directly, but M87 provides a natural laboratory to explore these effects in extreme conditions. Dark matter may also play a role. While it constitutes much of a galaxy's mass, its influence on the black hole or jet in M87 remains uncertain. Observations cannot yet confirm or deny its effect, leaving room for future discoveries. Plasma behavior in these conditions defies Earth-based replication. The gas near the horizon moves relativistically, interacts with strong magnetic fields, and experiences extreme gravity. Simulations continue to improve, yet approximations are still necessary. Each new observation refines our models and raises new questions, expanding the frontier of understanding. As you allow your mind to drift through these reflections, imagine standing at the edge of knowledge, peering into the unknown. M87's black hole shows where the known ends and the mysteries begin. Each unanswered question is not a barrier, but an invitation. The ring of fire, revealed by the Event Horizon Telescope, is not the conclusion. It is a doorway into deeper understanding, into the fundamental nature of gravity, space-time, and the universe itself. M87 did more than provide a picture. It created a reference point for the cosmos. Scientists could now return to it repeatedly, comparing new observations to that first image. Every fluctuation in the ring's brightness, every shift in the jet, every subtle change in polarization or accretion flow became a story about how black holes interact with their surroundings. The image turned an abstract object into a dynamic laboratory for the universe. The first image also emphasized the power of patience, persistence, and collaboration. Years, even decades, of incremental work across continents, its planes, and generations had converged into a single moment of clarity. It reminded the scientific community and the world that understanding extreme phenomena often requires slow, careful effort. Progress is not measured by flashes of insight alone, but by the cumulative work of countless people refining instruments, running simulations, analyzing data, and validating results. Beyond science, the image reshaped how people perceive the scale of the universe. The ring of fire, larger than our entire solar system, yet appearing as a delicate loop from Earth, made incomprehensible distances and masses feel tangible. It allowed humans to see the influence of gravity on a cosmic scale, to imagine the forces shaping galaxies and clusters, and to appreciate how even light bends and twists under the strongest pull known in nature. It also reminded us of the interconnectedness of knowledge and effort, the theories, simulations, and instruments that led to the image were built on centuries of work. Yet each new observation provided feedback that refined understanding across astrophysics. M87's black hole became a touchstone for testing relativity in extreme conditions. Studying plasma physics, exploring the behavior of magnetic fields and probing questions at the edge of quantum gravity. Culturally, M87 became a symbol of human curiosity and capability. It appeared in classrooms, science exhibits, media, and conversation, inspiring a new generation of learners and researchers. People who had never considered black holes before could now see one not just as a concept, but as a real object with measurable features and a dynamic influence on its galaxy. The Ring of Fire became a shared point of wonder, a reminder that even the most distant, extreme phenomena are within our reach if we work together. Yet, even with this extraordinary achievement, M87 left room for mystery. The shadow tells us about the event horizon, the ring about the accretion flow, and the jet about energy and magnetic fields, but it does not reveal the singularity, the ultimate fate of information, or the quantum structure of space-time. Each image is not the final answer. It is a doorway to the questions that remain. As you let this story settle in, imagine the balance between what we know and what we don't. M87 shows us the extraordinary things humans can measure, understand, and visualize. It also reminds us that the universe is larger, more intricate, and more mysterious than any single image can capture. The first glimpse of a black hole is both a confirmation of what theory predicted and an invitation to explore the unknown. M87's Ring of Fire does not shout or blaze with drama. It glows quietly, steadily, across millions of light years, carrying with it the story of gravity, light, and human perseverance. It is a bridge between imagination and reality, a reminder that patient, collaborative exploration can reveal the hidden structures of the universe, and that each new observation opens yet another door to understanding. Observing at infrared or optical wavelengths would open an entirely new window into black holes. The shorter wavelengths would allow astronomers to resolve even finer structures, potentially seeing smaller hotspots of plasma, sharper details of the photon ring, and more intricate interactions of matter and magnetic fields near the event horizon. Each new wavelength adds a layer of understanding, revealing phenomena that radio waves alone cannot fully capture. Future instruments may also incorporate space-based interferometry, extending the network of telescopes beyond Earth's surface. By placing observatories in orbit, the effective baseline of the array could far exceed Earth's diameter. This would result in an unprecedented increase in resolution, sharpening the image enough to separate the photon ring from the broader emission of the accretion flow, allowing scientists to directly test predictions of general relativity under the most extreme curvature of spacetime. With repeated observations over time, astronomers hope to create dynamic movies of black holes. These sequences would reveal the flow of gas, the orbit of hotspots, the twisting of magnetic fields, and the evolution of jets. Watching a black hole in motion would allow scientists to see how the environment near an event horizon changes on timescales of days, months, and even years. The variability itself contains clues about the physics at play, about turbulence, relativistic motion, energy extraction, and feedback between the black hole and its galaxy. Observing multiple black holes is another exciting frontier. M87 and Sagittarius A times are just the beginning. By comparing different black holes, those with faster or slower spins, stronger or weaker jets, and varied feeding patterns, scientists can begin to understand the diversity of these extreme objects and their influence on galactic evolution. Each observation expands our picture, not just of individual black holes, but of the universe as a connected system, where gravity, matter, energy, and time interact across scales from the smallest orbits to entire galaxies. Advances in computation, algorithms, and artificial intelligence will support this next era. Future image reconstruction may incorporate real-time simulations of plasma dynamics, magnetic fields, and light propagation. Machine learning could identify subtle structures and compare them against theoretical models, reducing uncertainties and uncovering patterns invisible to human analysis alone. As computational power grows, the images themselves may become more than static pictures. They may evolve into predictive maps, revealing not only what exists but how it changes and behaves. Through all these developments, one principle remains. Central black holes are dynamic laboratories for extreme physics. Observing them helps us test relativity under the strongest gravitational fields, explore the interplay of quantum effects with space-time curvature, and understand how energy and matter interact on cosmic scales. The first image of M87 was the first small lamp in a vast room. The future will be a network of lights, gradually illuminating every corner of that space, revealing not just black holes, but the physics that governs the universe itself. As you imagine these possibilities, it becomes clear that human curiosity, collaboration, and patience are as vital as telescopes, algorithms, and satellites. The journey that began with faint hints and indirect evidence has evolved into a fully global endeavor, one that will continue to expand our understanding of the cosmos for decades to come. The story of M87's black hole is not just about seeing the unseen, it is about opening the door to new questions, new discoveries, and new ways of thinking about space, time, and the forces that shape everything around us. As you linger at the edge of the event horizon, imagine the photons that travel uncountable light years to reach us. They carry the story of gravity, matter, and light, unaltered except by the laws that govern the cosmos. Each particle of light is a messenger, a bridge across space and time, delivering a snapshot of a place no human can ever physically reach. The black hole itself remains indifferent. It does not change because we observe it. It does not pause to reveal its secrets. It continues its quiet, persistent influence on everything around it, the swirling accretion flow, the twisting magnetic fields, the pulsating jet, and the distant stars of M87. And yet, by observing even a fraction of this activity, we touch the edges of understanding, glimpsing processes that shape galaxies and, ultimately, the universe itself. Think of the Event Horizon Telescope and its network of collaborators as humanity's extended senses, stretching across continents, oceans, and mountains. It is a testament not only to technological skill, but to collective curiosity, patience, and perseverance. Each carefully synchronized observation, each algorithm tested and refined, every frozen hard drive transported across the globe, all of it represents a slow, steady march toward knowledge. The first image of M87 was a single step, but it opened a path that will continue to unfold over decades, centuries even. As instruments improve, questions deepen, and new black holes reveal their secrets. The calm persistence of M87's black hole mirrors the rhythm of discovery itself. Science does not always shout its breakthroughs. Often it whispers them, waiting for careful observation, thoughtful analysis, and quiet reflection. The first ring of fire was not the end of the story. It was the opening note of a symphony that humanity will continue to play, one observation at a time. As your mind rests here, you might notice a sense of continuity. The photons from M87's black hole began their journey long before Earth existed in its current form, and long after our species is gone, they will continue traveling, carrying information about a distant galaxy across the silent expanse of space. The universe has its own patience, and we, through observation and understanding, have learned to move in rhythm with it. So let this image settle in your imagination, a glowing ring of light, a shadow of impossibility made visible, a reflection of both the known and the unknown. Let it remind you that exploration is never complete, that each discovery is a doorway, and that curiosity can stretch across the cosmos itself. The black hole endures, the jet persists, and the accretion flow continues its slow, mesmerizing dance. And we, watching from afar, continue learning, slowly but surely, guided by the quiet glow of a distant, ancient light. The story of M87 does not conclude here. It pauses in gentle anticipation, waiting for the next observation, The next question. The next generation of explorers. The universe is patient. So too can we be. As we continue to follow the light to wherever it leads quietly, steadily, with wonder, M87 is a story of patience, collaboration, and human curiosity, written in the light of photons that traveled millions of years across space. It began with subtle hints, fast-moving stars, hot gas, and bright emissions from the galaxy's center, clues that astronomers over centuries could only interpret indirectly. Through decades of observations and technological improvements, these scattered pieces slowly came together, revealing a coherent picture, a supermassive black hole at the center of M87, influencing its surroundings and shaping the entire galaxy. The idea of observing directly near a black hole's event horizon demanded a technological leap, connecting radio telescopes across the globe, synchronizing them with atomic clocks accurate to nanoseconds, and capturing vast amounts of data to be processed later. No single observatory on Earth could see the shadow of the black hole alone. But when the instruments worked together, Earth itself became a planet-sized telescope, capable of detecting the elusive silhouette of M87's black hole. This achievement exemplifies the power of global cooperation. Astronomers, engineers, programmers, students, and specialists from countless fields collaborated across continents and time zones. Every observation, every algorithm, every simulation contributed to producing the first image, a glowing ring encircling a deep central shadow, the first direct view of a black hole's event horizon. The image did more than confirm the black hole's existence. It validated Einstein's general relativity under extreme gravitational conditions, where space is curved, time flows differently, and light follows warped paths. The bright ring represents hot plasma orbiting the black hole, Doppler boosted as it moves toward Earth, while the central darkness marks the event horizon, the boundary from which no light escapes. For the first time, theory and observation converged in a tangible visual reality beyond science. M87 captured the imagination of the world. People who had never studied astrophysics now had a visual reference for something previously abstract. It showed the scale of the universe in a way numbers alone cannot convey. The ring spans more than our entire solar system, yet appears as a delicate loop. The black hole's influence is apparent not just locally but across its galaxy, with jets of energetic particles carrying matter and energy thousands of light years outward, regulating star formation and shaping the environment. The image also revealed the behavior of magnetic fields, confirmed mechanisms theorized decades earlier for how black holes extract rotational energy to power jets, and connected the physics of the event horizon to the larger cosmic structure. It provided the first glimpse into phenomena previously only modeled mathematically: turbulence in accretion flows, frame dragging, relativistic motion, and energy feedback on galactic scales. Yet the first image of M87 was not the end of the story. It opened new questions. How does the jet maintain its structure over thousands of light years? How are particles accelerated to near light speeds? How does turbulence and plasma behavior influence the accretion flow? What happens to information that crosses the event horizon? How exactly does quantum gravity operate near a singularity? These questions lie at the boundary of known physics, at the edge where the universe still remains mysterious. Looking forward, the future of black hole observation promises even greater clarity. The Event Horizon Telescope will expand with more observatories across currently unfilled regions, improving coverage and resolution. Higher frequency observations will probe closer to the horizon, revealing finer details. Space-based interferometry could dramatically increase baseline distances, enabling sharper images and isolating the photon ring itself. Multi-wavelength observations, combining radio, infrared, X-ray, and gravitational wave data, will provide a holistic view of black hole environments. Advanced algorithms, machine learning, and simulations will refine reconstructions, revealing the dynamics of matter, magnetic fields, and space-time with unprecedented precision. Observing M87 repeatedly over months, years, and decades will allow scientists to track changes in the accretion flow, magnetic fields, and jet behavior, offering insight into the stability and variability of these extreme environments. Studying other supermassive black holes will provide comparative data, revealing patterns in spin, feeding behavior, and interaction with host galaxies. Each discovery adds a layer to the ever-expanding understanding of the cosmos. The story of M87 is a testament to human persistence. It was not the achievement of a single person, instrument, or country. It was the result of thousands of contributions, spanning generations, languages, and continents. It demonstrates that major scientific breakthroughs often arise from decades of preparation, collaboration, and incremental progress rather than sudden inspiration. The first image of M87 reshaped not only science but culture. It made black holes tangible, accessible, and awe-inspiring. It inspired students, researchers, and the public alike. It reminds us that the universe, vast and extreme as it is, can be studied and understood with patience, ingenuity, and cooperation. The black hole itself remains quiet, consistent, and steady. Its accretion flow brightens, the jet pulses, but the core persists as it has for billions of years. Observing it is a reflective act, a way to engage with the universe at the edge of what we can know. Each photon captured carries a story from millions of years ago, guided by gravity, plasma, and magnetic fields, and finally, interpreted by human ingenuity. M87's ring of fire, its shadow, and its jet represent a doorway. They are an invitation to explore, a reminder that discovery is never complete, and that the unknown is not a limitation but a horizon. The journey continues, patiently, steadily, and quietly, expanding our understanding of the cosmos, one observation at a time. Every new image, every new dataset, every new telescope adds another ring to the tree of knowledge, revealing not only what we know but also the vast space of what remains to be discovered. M87 is more than a galaxy, more than a black hole, more than an image. It is a testament to curiosity, perseverance, and human collaboration. It is a story still unfolding, a journey with no final chapter, quietly waiting for the next generation to step through the door. Guided by light that has traveled across the universe to meet our eyes,